Good evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the 2021-22 winter forecast. This is video part 3. So this is part 3 of the forecast, and this will be the final and concluding part for our official winter forecast this year. On the cover of part 3 video, I kept things in line with more of a wintry scene. This is the infamous Polar Express train, and a lot of snow there as it was making its way down the track in the movie. Very good movie, especially around Christmas time. But again, keeping in the spirit of a winter weather and snow, decided to throw this one in for part 3. So there's a lot to talk about tonight. Now, we've already talked about everything that is in red font on this slide. For part 3, I'm going to move into a discussion on the NAO, or North Atlantic Oscillation. We'll talk about the sudden stratospheric warming, the stratospheric polar vortex, and then I'll move into a discussion on sea surface temperature anomalies, the importance of those, solar activity as well. And then I will move into the discussion on my weighted forecast factors for this upcoming winter season, my final thoughts, and then the actual forecast weather maps. Again, as a reminder, the winter forecast covers a period, meteorological winter period, from 1 December to 28 February. So let's kick things off in this final part 3 video for the winter outlook, and let's talk about the North Atlantic Oscillation. The NAO generally has 2 phases. These are the positive and negative phases. If you look at the graphic on the left, with a positive phased NAO, you typically have a strong Icelandic low across the North Atlantic, so very strong low pressure, and very strong high pressure to the south. And that pressure gradient between that strong Icelandic low and the Azores high generally leads to a faster moving, highly zonal west to east Atlantic jet stream. As a result, we typically see more of a milder conditions along the southeast and mid-Atlantic coast in a positive NAO phase. We typically see cold and more sea ice up in the northern latitudes as well. Now with the negative phase of the NAO, the bottom left-hand graphic, we have a little bit of a difference there. We have this large blocking upper-level ridge into Greenland with a negative NAO. We typically have upstream of that ridge over the eastern U.S., the eastern seaboard. We generally have colder than normal temperatures in a negative phase NAO, along with snowier or above normal precipitation with an enhanced trough off the U.S. East Coast. And we generally have a weak Icelandic low with a negative NAO up to the north there, and a weaker Azores high, which results in a weaker overall Atlantic jet stream during the negative phase of the NAO, and that generally leads to a more meridional structure to the tropospheric polar front jet stream. I look at the graphic on the right. That generally shows you the ups and downs, the positive versus negative phases of the NAO. The red spikes in the positive territory, that indicates the positive phase of the NAO. The blue inverted spikes below the zero value line there indicate the negative phases of the NAO. So if we look back to 1980 on that graphic on the right, you'll notice some periods were dominated more by positive NAOs, such as the 1989-90 season, as well as the 92-93 season. Additionally, we had a strong El Nino around that time period, by the way. And then we have a very strong positive NAO 2018-2019 winter season as well. Some of the more recent negative NAO phases included last winter season, the 2020-21 winter season, as well as the 2019-20 winter season. So again, ups and downs. We can look at the trends of the NAO with that graphic on the right. If we look at the actual observed 2020-21 winter season NAO, the blue bars there on the left, if they are above that zero line in positive territory, that generally means the NAO is positive. If you see those blue vertical lines below the zero line in the negative territory, that's the negative phase of the NAO. And for last winter in particular, The graphic on the left goes back to the last few days of October. Really, the end of October through the 1st of December, we had a fairly positive NAO phase. But then as we got into December and especially January 2021 into February, the early parts of February, we had a predominantly negative NAO. Okay. The strong upper level ridging was occurring especially on the North Atlantic side into Greenland and northeastern Canada last winter season, sending abnormally warm temperatures into higher latitudes. All right, moving on to the sudden stratospheric warming topic. By the way, the graphic on the left is courtesy of Dr. Amy Butler, who does extensive research on the stratosphere and the phenomenon in the stratosphere, such as this polar vortex and the sudden stratospheric warming events. The graphic on the left shows the disruption of the stratospheric polar vortex in early January of 2021. And then those lines beneath those three diagrams generally indicates how the temperatures change within the stratosphere over time. And so initially around December 26, 2020, the polar vortex, basically we had some waves that propagated, vertically propagating waves that moved up from the troposphere into the stratosphere that weakened the stratospheric polar vortex. And what we had was what's known as a sudden stratospheric warming event. In general, what we have is that orange line there in that graphic below the polar vortex depictions. The orange line there at the bottom left, that generally indicates how over time in late December we had the stratospheric westerly winds begin to slow as the temperatures increased or warmed in the stratosphere. And by early January, the winds actually reversed sign and the temperatures peaked by around January 5th, 2021. If you look at the overall changes of the polar vortex there, you'll notice the purple shading there indicating the polar vortex. Over time, by January 15th, the polar vortex had basically split into two specific lobes by mid-January of 2021. So overall, sudden stratospheric warmings, these are significant. They occur when the polar stratosphere warms and the winds that normally flow from west to east around the pole at about 60 degrees north latitude at about 10 millibars, which equates to about 18 miles above the surface. These west to east winds weaken dramatically and even reverse direction and become more easterly. And these sudden stratospheric warming events typically occur 6 times per decade on average. And this leads to a weakening of that stratospheric polar vortex. So this is just a great example of a sudden stratospheric warming by that graphic there in the bottom left of the slide. And that orange line, notice that spike up in the orange line in the temperatures in the stratosphere. Now, what does this have to do? Sudden stratospheric warmings, what they do is they tend to weaken the stratospheric polar vortex. Now, the graphic on the left shows what you typically have with a stable polar vortex. You typically have this cyclonic spinning circulation over the Arctic areas, over the poles in the wintertime in the northern hemisphere. And generally with a stable polar vortex, it remains over that polar area, and really the coldest air remains contained up over the higher latitudes in the Arctic. But if we get a weaker polar vortex, it can be either displaced off the poles or it can be stretched out. And that results, when you get this weakening of the polar vortex, that results in a more wavier jet stream where you get these large segments of mid-latitude air being advected into the higher latitudes up towards the Arctic region, and you get these much colder troughs that are associated with the tropospheric polar front jet stream that move from that Arctic area with a direct connection of cold air from the Arctic down to the United States, parts of Europe, into Asia. Look at the graphic on the right, generally shows you an Arctic connection, that blue shading in that graphic on the right. You got this very deep trough that's positioned over the upper Midwest, right on down into the southeastern United States. And it's a direct connection. Notice that blue shading goes all the way up to the top of that graphic on the right, all the way up to the Arctic region. So we have direct flow from the Arctic in this case. And notice that you have very strong ridging over the northeastern Pacific in this case, into western Canada. All that warm air is being advected into higher latitudes. So in general, the location of coldest air, it's never the same with each weekend polar vortex event. There are some rules of thumb that Dr. Judah Cohen has come up with. In general, I want to also mention that surface effects, those colder temperatures, are typically not felt until 3 to 4 weeks, sometimes on the order of 30 days after the event, after the polar vortex weakens. And the Arctic Oscillation, the AO, tends to average negative for a period of 4 to 6 weeks following a weak polar vortex, a weakening of that polar vortex, accompanied by colder than normal temperatures. I got that directly from the just amazing research that Dr. Judah Cohen has done. So I'm definitely providing the citation there from his research. Now, if we look at the polar vortex strength factors, again, this research is conducted by Dr. Judah Cohen of the Atmospheric Environmental Research, AER. He has determined that polar vortex elongations or stretching of the polar vortex generally favor the coldest temperatures to be located in the eastern northern hemisphere, including eastern North America. Splitting of the polar vortex usually favors the coldest temperatures to be over Siberia and Europe. So it's a big deal whether we're talking about a elongation of the polar vortex, a stretching of it, or an actual splitting into multiple pieces of that stratospheric polar vortex. The graphic on the left-hand portion of the slide, generally Dr. Judah Cohen has done the research and increased autumn snow cover in Siberia along with that strengthening jet stream. You get some upper level ridging into the Arctic areas, and that tends to that transfer of vertically propagating waves from the troposphere to the stratosphere tends to weaken the polar vortex, and ultimately end up getting colder winter weather in eastern U.S. and Europe in the wintertime. A graphic on the right there shows a significant change in the pressure there. The maroon shading in the graphic on the right shows the 10 millibar hectopascal height for the 6th of January 2019. This was another sudden stratospheric warming event. You'll notice up at 18 miles above the ground at 10 millibars, the maroon shading indicating very much above normal temperatures in the stratosphere. And what happened was the polar vortex in this case split into two specific lobes. One is located there over northern Europe, and the other is located over in the vicinity of eastern Canada and the Hudson Bay area. All right, now I dig some of these important facts about the polar vortex out. Just want to again show you some major impacts here with this. This is a real wild card in the wintertime. For example, these stratospheric polar vortex weakenings just don't occur every winter. There's no guarantee of these occurring every winter. So in general, the polar vortex the splits tend to favor colder weather in Europe and increased heavy snow and nor'easters along the U.S. East Coast. The polar vortex displacement is going to favor colder temperatures but less snow in the eastern U.S. with milder air in Europe. And Siberia is cold regardless of whether we have a polar vortex split or a displacement. And all that data, again, comes directly from Dr. Judah Cohen's research. I will show you a great website to check out his latest blogs as well. Now, when the wave activity flux, that energy is absorbed, there's a couple things that happen. Either the wave activity flux or energy is either absorbed or it's reflected. And this is going to make a huge deal. It's going to be a very significant deal as far as the type of weather we typically get. So, for example, when wave activity flux is absorbed, Greenland blocking occurs. You tend to get a negative NAO, and you get 2 weeks of colder temperatures over the U.S. Now, the source of that data comes from research conducted by Kretschmer and et al. In 2018. Now, when that wave activity flux is reflected and not absorbed, you typically get blocking to occur near Alaska with relatively cold temperatures across much of Canada, the eastern United States, and Central Asia. And that data is pulled directly from research by Kretschmer et al. 2018. In general, when that wave activity flux is reflected, it's not associated with a negative NAO. The troposphere shows a rapid response of short duration, effects usually lasting only days to 2 weeks. And this type of event, by the way, the reflected wave activity flux polar vortex event, resulted in historic cold across the eastern U.S. in early January 2018. I remember that very well. It was a very frigid New Year's Eve, New Year's Day, first couple days of January, and that sustained cold preceded a major snowstorm that hit places with snow that don't normally get snow, places like Savannah, Georgia, and Charleston, South Carolina, right up here into the Hampton Road cities in eastern Virginia. We got socked with a good 7 to 10 inch snowstorm with that particular event. Additionally, if I show you the example here on the left, the graphics on the left generally shows the orange coloring indicates initially on January 1st, 2009, we had a pretty concentric polar vortex by that orangish shading there on the far left, very circular in nature over the pole. But over time, that polar vortex weakened by February 2nd, 2009, where you had two distinct lobes of the vortex. The vortex was displaced off the polar area, and you have one position over eastern Canada and one position over Europe, Central Europe area. So this is an example, this graphic, of the polar vortex and how it can go from one piece to two pieces, or we call them lobes. And when those lobes tend to travel down from the Arctic towards the middle latitudes, they transport very frigid air to the middle latitudes in both North America as well as Asia. So the 2009 and 10 winter season, by the way, it had an easterly QBO. An easterly QBO, which I talked about in part 2, the part 2 video, the winter forecast, easterly QBOs favor strong polar vortex disruptions. Now, Siberia is generally cold for, again, both splits and displacement. And I did cover the last two bullets there as well, whether we have wave activity flux absorbed or whether we have it reflected. All right, so here's Dr. Judah Cohen. I went and contacted him to make sure he was okay with me citing his research in this video. And he was gracious enough to say, absolutely, you can go ahead and use my research as long as you cite it. So there's a picture of Dr. Cohen. He also has developed this Siberian snow cover model on the left. Again, he believes that the Siberian snow cover, that plays a major role in the month of October, as well as the Arctic sea ice and the Barents-Kara seas. Whether that's low, that generally tends to lead to a chain reaction, or what's known as a feedback mechanism. And you can see that on the left there, the Siberian snow cover model. Generally, if we get increased snow cover extent across Siberia in October, that tends to lead to a positive feedback to colder temperatures, surface temperatures. That will then strengthen the Siberian high pressure system in November, which then will help to assist in the amplification of the tropospheric jet stream, which enhances what's known as poleward heat flux and that vertical wave propagation that tends to move from the troposphere to the stratosphere and disrupt the polar vortex and weaken it. So once that stratospheric polar vortex weakens in the month of December, you get this sudden stratospheric warming, and then in January that leads to stratospheric circulation anomalies propagating back down into the troposphere where we live. And by February, you're looking at negative AO conditions developing in the troposphere. The graphic generally in the bottom there, the website link is there to AER for Dr. Cohen. He does weekly blogs, and they're amazingly informative. I really highly encourage you to follow his research and his polar vortex and Arctic oscillation and winter weekly blogs that he posts on that website there indicated. So please check him out. He's a great resource, and I've learned so much from him. and all the research he's done on this particular topic. Now, if we look at Arctic sea ice extent, in general, what we're looking at here is we have the highest minimum amount of Arctic sea ice since the year 2014. We're not quite as low as, say, 2012. In 2012, we had record low Arctic sea ice. So we're basically sitting, and I have some statistics here in a minute. But in general, if you look at the graphic on the right, the sea ice extent as of the 23rd of September 2021, the white coloring is the actual Arctic sea ice. And that little lighter colored orange line represents the 1981 to 2010, where the ice edge was typically located over that 30-year period. So again, we've reached the lowest sea ice amount in the Arctic, and it's the highest since the year 2014. In general, why is this important? Well, less sea ice in the Arctic leads to warmer temperatures due to solar radiation being absorbed by the unfrozen water. Generally, if you have a snow or ice surface, it tends to lead to increased reflectivity of incoming solar radiation, and that leads to colder overlying air mass. But when that ice melts, we no longer have that higher reflectivity, or what's known as albedo, to keep the temperatures cooler in the Arctic. So overall, this leads to warmer overlying air temperatures in the Arctic. And with the high Siberian snow cover plus that low Arctic sea ice, what Dr. Judah Cohen's research has shown is that tends to lead to a weaker stratospheric polar vortex and ultimately a negative Arctic oscillation with time. Okay, so as promised, here's the top 10 lowest Arctic sea ice extent years. I circled on the data there on the left, I circled that the Arctic sea ice minimum this year ranked 12th all time on the list. 2012 had the least amount of Arctic sea ice. And even last year in 2020, we had the second least amount of sea ice. So we're sitting at number 12 for 2021 for this year in September. The graphic on the right is from Rutgers, the Global Snow Lab. Check out the Global Snow Lab from Rutgers. It's a really good site. The orange shadings there on the graphic on the right indicate areas that are snow covered right now. So parts of northwestern Canada into Alaska, Greenland, some of the higher land areas there in the Arctic are snow covered. The little bits and pieces of Siberia are snow covered as well. And again, the main point, in accordance with Dr. Cohen's research, extensive Eurasian snow cover in the fall results in a stronger Siberian high setting up, increased polar heat flux, a weaker polar vortex over time, and that negative Arctic oscillation for the wintertime. All right, so I'm going to give a couple examples here of a strong polar vortex winter versus a weaker polar vortex winter. So we look back at the year 2019-2020 winter season, just a couple winters ago, and we had this record strong cold stratospheric polar vortex. This polar vortex all year was just strong, and you can see the graphic on the left, the purple coloring and those white arrows, very symmetrical shape. We're looking down from above the North Pole in that graphic on the left. And so just extremely strong polar vortex all winter long, which led to an extremely positive Arctic oscillation, stronger high zonal jet streams across the northern oceans, the oceans of the northern hemisphere. Wave activity flux was unusually low, so we just didn't have much energy transfer from the troposphere into the stratosphere, which allowed the polar vortex to remain relatively undisturbed and very stable. Kept all the Arctic air bottled up to the Arctic region itself. And again, it was accompanied by a positive phase of the Arctic oscillation in the 2019-20 winter. Look at that graphic of departures from normal on the right for the United States between January 1st and January 31st, 2020. Wow. You're looking at temperatures on the order of 5 to 10 degrees above normal all across the eastern U.S., basically from Indiana, Michigan, Tennessee, to the East Coast, parts of New York State and New England, 5 to 7 degrees Fahrenheit above normal for the month of January alone. I remember this winter, and I remember how mild it was. I was traveling back to Southeast Virginia, and right before New Year's Eve, the temperature that day was 76 degrees. It was just, yeah, you could be out in shorts and a t-shirt. That's how warm it was. And now look at this. This is the opposite effect. You know, we had the very strong polar vortex in 2019-20 winter, but then you had the weakened polar vortex episodes. This happened to be on the left, this is January 2014, and on the right, I'm showing you a graphic from last winter in February of 2021. And look at the purple shading. This is the typical effect you see, 30 days to 40 days after the polar vortex weakens. You get this anomalously cold air that filters into the eastern part of the United States. In an example on the right, the coldest air remained a little bit further west than usual, back into the Midwest and to the deep south into Texas in February 2021. But in general, you can see the purple shading indicating temperature departures on the order of 10 to 15 degrees below normal, 10 to 15 degrees Fahrenheit below normal in these cases after a weakened polar vortex. But these are a couple different winters, 2014 on the left and 2021 on the right, just showing you the difference between, that graphic on the right and a strong polar vortex winter versus a weaker polar vortex winter. Very big differences in the type of temperatures we see. If we look at the latest European model polar vortex forecast, the graphic on the left shows that maroon shading and generally some warming on the order of 8 to 10 degrees Celsius up over the Arctic areas forecast for the later part of October. This is something to watch. I have noticed some extensive ridging already that's been occurring this week into higher latitudes. We have seen a negative NAO already. We have seen warming into Greenland, and we've also seen warming into central Canada up to the higher Arctic regions, higher latitudes are already. So, that's real interesting. We got signs by the models of warming that's going to be occurring this winter already. This type of warming at 10 millibars or 18 miles above the surface, again, that's known as that sudden stratospheric warming, which I covered, which leads to a weakening stratospheric polar vortex. We'll watch these model trends between now and November to see if they remain consistent. One thing to note about models and the handling of stratospheric warming events, they generally struggle predicting impacts of the stratosphere and the troposphere coupling. And what I mean by that is that energy transfer between the two spheres until the signal typically reaches the tropopause below about 100 millibars or hectopascals. Again, that last note about models and how they struggle to predict impacts of the coupling is, thanks to Dr. Judog Cohen and his amazing research. Now let's move on to the topic of sea surface temperature anomalies. On the left, I have a graphic of the temperature anomalies from September 2020. On the right is this year, September 2021. Now, the orangish shadings generally indicate above normal sea surface temperature anomalies, above normal water temps, basically, and the blue shading indicates below normal water temperatures. Okay. In general, we see the graphic on the left compared to the graphic on the right last year versus this year, this time of year, and you'll notice that the area of warmer than normal water is a little bit more concentrated, and the band is more narrow across the North Pacific Ocean this particular year. Additionally, you'll notice there's a area of cooler water this year right off the immediate Pacific Northwest, off of Washington State, Oregon, and Northern California that was not there last year. Additionally, pay attention to the equatorial and eastern and central Pacific, and notice the blue shading indicating the La Nina. Last winter, the graphic on the left in September 2020, you can see that La Nina. It was more concentrated. The temperatures were cooler than they are currently compared to this year. Okay, so something to keep an eye on. There was overall more widespread warmer than normal water in the northeastern Pacific in the year 2020, in September of 2020, as compared to this year in September of 2021. And that graphic on the right with the colder temperatures there situated right off the Pacific Northwest, that's indicative of a negative Pacific decadal oscillation, and that would favor troughing over the eastern Pacific, countering what we would typically see with La Nina. La Nina would give us more of the upper level ridging. So that's going to be interesting to watch how these water temperatures, how this unfolds. All right, moving on to the 2020-21 winter sea surface temperature anomalies. This was last winter. This first graphic is from December, and it shows clearly the La Nina conditions across the equatorial eastern and central Pacific. So I just wanted to show you how the temperatures looked last winter. This is January of 2021. You'll notice the La Nina, the coloring of that blue shading there. It tends to spread a little bit further to the west. And also, you'll notice over time as I move to February how that La Nina is weakening. Some of those cooler waters initially we saw in December of 2020, by February 2021, you're starting to see more of the orange shading, so some warming conditions in the eastern equatorial Pacific Ocean, which is resulting in more of a trend towards El Nino neutral conditions or ENSO neutral conditions. If we look at sea surface temperature anomalies in the past, especially across the northeastern Pacific, February 2014, we had what was known as, they call it the warm blob. You can look this up and Google it. We had water temperatures on the order of 2.5 degrees Celsius above normal in the northeastern Pacific, and that played a huge role. If you look at these anomalous areas of warm water, they could play a role in the polar front jet stream configuration. Trough versus ridge. Ridges tend to set up over anomalously warmer water, and this happened during the winter of 2014-15. Warmer sea surface temperatures in the Pacific and Atlantic Oceans, they generally help to anchor ridging and positive height anomalies in those locations. So what I'm getting at here is these sea surface temperature anomalies can really alter and help to transform the long wave pattern or how the polar front jet stream sets up. El Ninos tend to favor stronger Aleutian lows, by the way. I just want to throw that out there. Of course, this winter we're looking at a La Nina, so we would typically see more of that ridge in the Gulf of Alaska. Now, colder sea surface temperatures in the North Atlantic Ocean, they tend to yield stronger jet stream across the Atlantic and a positive Arctic oscillation, and that's mainly due to that stronger temperature and the pressure gradient between the Icelandic low in the North Atlantic and the Azores high. Stronger temperature gradients across Asia tend to fuel a stronger zonal west to east Pacific jet. Additionally, that cools the sea surface temperatures in the North Pacific. And this very highly zonal west to east jet, a very strong jet, if you have a strong temperature gradient across Asia, that tends to lead to milder Pacific air, generally moving from the west to the east coast of the United States, and milder winters of the past. So it's always important to keep an eye when we look at the winter forecast on the temperature anomalies across the Pacific Ocean. Not only in the lower latitudes with El Nino and La Nina, but also in the higher latitudes, in more in the middle latitudes, because this is the upstream area that is going to have a great impact on our temperatures for the winter season, as well as the jet stream configuration. I also want to talk about solar activity. We're currently sitting very low on sunspot activity, overall solar activity in general, as we enter into solar cycle 25. Now that red line gives you a prediction of what's expected as we enter into solar cycle 25. So from the year 2022 on through the year 2025, we expect the solar activity to definitely increase with more than 100 sunspots possible. Keep in mind that the solar cycle operates generally on the order of every 11 years we get a more active sun. Now you might think to yourself, what does this have to do with the winter forecast? What does this have to do with the weather? Research has indicated that we see more frequent high latitude blocking, which is affiliated with that negative North Atlantic oscillation during low solar activity periods. Now some of the greatest East Coast snowstorms have actually occurred during low solar winters. We can go back to February 2010. Boy, that was a big winter for folks in Washington, D.C. and parts further northward as we had multiple nor'easters, sometimes That period in February 2010 was known as Snowmageddon. December 2009, we had low solar activity in the winter. Another area of East Coast snowstorms, another time period of great East Coast snowstorms. And then January 1996 as well. So you get the high latitude blocking in the North Pacific and North Atlantic. And that tends to send that warmth and the energy from the troposphere to the stratosphere, and can also tie into the strength of the stratospheric polar vortex. So here's the questions to ponder for the upcoming winter. Okay, this is a very difficult forecast. Pacific, whether we're talking about La Nina, the MJO, the QBO, the PDO, EPO, and PNA, those teleconnection influences, will they be more dominant this winter? Will the Pacific dominate is what I'm getting at. Strength of La Nina, very important. If this La Nina turns out to be weak as forecast, then we expect less impacts for the United States weather as far as temperatures. But if we have a stronger La Nina, then we can expect greater impacts. A stronger La Nina plus a positive Arctic Oscillation, or AO, would definitely yield a milder winter for the eastern U.S. The next point I want to talk about is the Atlantic teleconnections. You know, the AO or the NAO. Will those teleconnections be more dominant? Will their influence be more dominant over the Pacific? And then we, of course, always have the wild card in our winter forecast, and that is the stratospheric polar vortex, the Arctic influence. Will we see that be more dominant this winter? Or will we see a hybrid of all three regions, the Pacific teleconnections, the Atlantic teleconnections, and the Arctic polar vortex, the stratospheric polar vortex? And also, how does this impact the tropospheric polar front jet stream configuration? If we have a stronger jet, it's more zonal typically. If we have a weaker jet, it becomes more meridional, where we have much greater dips in the jet stream and transport a much colder air from higher to lower latitudes. Additionally, we got to look at, what are we looking at this winter as far as combination? Will there be a combination of teleconnections? Or does one teleconnection dominate a part of winter or the entire winter? Constructive versus destructive interference scenario. Will the teleconnections be working with each other or against each other? All of these factors make winter forecasting, again, very challenging. We can use past analog methods, such as pattern recognition, but that's not a guarantee to pan out with the same outcome, as the slightest changes can lead to different results or a different outcome. Chaos Theory by Edward Lorenz, I highly encourage you to take a look at that. A butterfly flapping its wings in Brazil. Just the slightest perturbations in the airstream can lead to very unpredictable outcomes in longer range forecasting, such as seasonal forecasting. We have seen relatively mild winters the past 3 years here in the Mid-Atlantic, specifically southeastern Virginia when I look at my data. So we're due for a colder winter. Natural law of equilibrium says eventually things balance out, right? Isaac Newton said it best when he said, for every action there is an equal and opposite reaction. And finally, I don't have it on here, but not all La Ninas are ever identical each winter. So you don't always get the same weather with the La Nina patterns. So here are my weighted forecast factors for this year's winter outlook. And this is focused primarily on the Mid-Atlantic. But I will show you my United States forecast at the very end here. So for the MJO, the Madden-Julian Oscillation, what are we predicting for the predominant phase is it to be more in a null phase similar to last winter, with minimal impact expected from the MJO. Now the quasi-biennial oscillation, the QBO, forecast to be negative, so that would indicate easterly zonal winds in the equatorial stratosphere. This would generally indicate easterly QBOs favor colder than normal temperatures for the Mid-Atlantic in the winter season. And my weighting on this for the factor is a weighting of 3 on a scale of 10. That just shows you the significance of how much weight I'm placing in these various factors. The Pacific Decadal Oscillation forecast, that has to tie in more with the sea surface temperature anomalies there across the Northeast Pacific. We're expecting a negative phase, and in that case we would expect warmer than normal temperatures for the mid-Atlantic. But that's going to really be dependent on the position of that upper level ridge in the Gulf of Alaska. How close does it get to western Canada and the west coast of the U.S.? Or how far back towards the west is that upper level ridge located? Additionally, La Nina. Right now, it's looking like it will be a weak to possibly low-end moderate La Nina this winter, per the latest Climate Prediction Center forecast. Now, a weak to moderate La Nina will generally lead to near average temperatures and precipitation, if weak. But warmer and drier conditions if it's stronger. And I factor La Nina into this winter forecast. I give it a factor of 5 on a scale of 10. And then the Eastern Pacific Oscillation. We're expecting a negative phase to that. That generally equates to a ridge in the Northeast Pacific, and we'd expect near normal to possibly slightly below normal temperatures with a negative phased EPO. Moving on to the Arctic Oscillation. Now, I'm expecting that to be negative, especially with a colder period associated with the weakening state of the polar vortex in late December through January. The AO, I'm giving a factor of 3 on a scale of 10, but I did put in bold that the AO is a major wild card in the winter forecast. The North Atlantic Oscillation, I'm expecting it also to be in more in a negative phase than a positive phase, with a colder period and that with more active storm track primarily in late December through January. Again, a factor of 3 on a scale of 10 for the NAO, and again, that is also a major wild card. The Stratospheric polar vortex, expecting weakening of it in December with major impacts in January to the eastern United States, at which time we'll see a very cold period. So I'm factoring, giving it a factor of 4 on a scale of 10. But again, the stratospheric polar vortex, there's no guarantee it's going to weaken. And predicting the behavior of it is very challenging each winter. Now, the Arctic sea ice, again, as I mentioned earlier, is the 12th lowest on record through the 23rd of September, 2021. We'd expect decreased reflectivity or albedo from the snow and ice-covered surfaces, release of warmth to the overlying air mass in the Arctic. So low Arctic sea ice tends to lead to colder than normal temps across the eastern United States, as well as the mid-Atlantic. Now, the low solar activity, we're still in a lull period, as I showed right back here. See where we're at. In a low activity period, we'd expect to increase in high latitude blocking across the North Atlantic and North Pacific. That will lead to colder temperatures and the predominance of a negative NAO this winter. So my final thoughts are this. I've got a few slides of final thoughts. It's so in-depth. I've done a lot of research before I put this together. A negative PDO, a weak to moderate La Nina, and that negative EPO, all three of those teleconnections on the Pacific side could actually work together in a constructive interference evolution, resulting in a ridge in the Gulf of Alaska. Now, where does that ridge axis actually set up? If it's too far to the west, then you'll get a trough over the western U.S., and most likely you'll get a ridge further downstream and perhaps milder temperatures over the Midwest and eastern U.S. That's one question to really ponder. The low solar activity favors high latitude blocking over the North Pacific and North Atlantic Oceans, while easterly QBO favors colder temperatures for the eastern U.S. 3 teleconnections, when I did my analysis of this, 3 of the teleconnections favor a warmer than average winter, while 3 teleconnections favor a colder than average winter. So I'm like split 3 and 3 down the middle. I looked at 6 teleconnections, and I've got 3 favoring warmer than average winter and 3 favoring a colder than average winter. But here are the wild cards. They are the AO, the NAO, and the stratospheric polar vortex behavior. Those really are the 3 wild cards in the upcoming winter forecast. They're going to play a large role in the winter temperatures. As I mentioned before, the AO and the stratospheric polar vortex strength are directly correlated with each other, while the NAO depends on the North Atlantic sea surface temperature anomalies, that pressure gradient between the Icelandic low and the Azores high, So in general, a stronger jet stream is going to result in a more zonal west to east pattern across the oceans. If in the Pacific we have a high zonal, a very strong jet in the Pacific, that generally tends to lead to milder temps for the U.S. in winter. A weaker jet stream, on the other hand, results in a more meridional jet stream and a transport of much colder air from the north into the U.S. So again, there is a lot of thought I'm putting into this forecast. My overall final thought, though, is I think the coldest air is going to stay back to the northwest of the mid-Atlantic. That's not to say we won't see very cold periods, especially in January with a weakening polar vortex, a negative AO, a negative NAO. So we are going to see those colder than normal temperatures in the mid-Atlantic in late December and January due to the effects of the weakening polar vortex. That's the way it looks right now. La Nina will most likely be weak, but it could be possibly moderate, low-end moderate. Then I'm expecting that La Nina to weaken towards neutral ENSO conditions in February. This could be quite similar to last winter season. I really don't see much difference between La Nina last year and this year. The latest models are forecasting the stratospheric polar vortex to weaken in December, leading to a colder January across the eastern U.S. Now, these are the latest models, and they could change. So that's very important to make that note to everybody watching this. Just because the models say, hey, the stratospheric polar vortex is going to weaken in December right now, that generally we have to watch for the consistency and the trends of those models. So that is subject to change. Increased probability of a weakening polar vortex based on the La Nina, as well as a easterly QBO. La Nina, 60 to 75% of winters with La Nina result in a weakening stratospheric polar vortex. Easterly QBO, again, favors a sudden stratospheric warming event leading to that weakening polar vortex. Now, a stretching versus a splitting makes a big difference in that polar vortex as far as sensible weather goes. Stretching is going to focus the colder temperatures more in eastern North America, okay? Eastern Canada down to the eastern U.S., while a splitting polar vortex typically focuses the brunt of the coldest air into Europe. So this is really huge, the after effects of the polar vortex weakening. Does it get stretched or elongated, or does it split into multiple lobes or pieces? And here is my forecast. All right, here's the forecast for Spot On Weather. We're expecting near normal temperatures and drier than normal conditions during the 2021-22 winter season across southeast Virginia and the mid-Atlantic. We will see periods of Arctic air, but temperatures overall are going to average out close to normal, similar to last winter. So just want to throw that out there. Based on all of these indicators, the climate drivers, the teleconnections, this is what we're seeing right now. We can expect accumulating snow on the order of 2 to 4 inches, possible between 20 January and 10 February for Hampton Road cities. And this is in line with climatology as well as the coldest temperatures of winter moving south in January associated with the weakened polar vortex. And here is the map showing the coldest temperature departures, the forecast for the temperature departures for winter time. Coldest temperatures over the upper Midwest into the northern plain states, near normal temperatures for mid-Atlantic up to New England, and then the warmest temperatures generally from Texas stretching along the Gulf Coast into Florida and Georgia. And then the forecast precipitation departures. We're expecting below normal precip for the winter months there from South Texas up through North Florida into the mid-Atlantic. Wetter than normal conditions over New England, and then wetter than normal conditions from the high plain states all the way into the Ohio River Valley, and below normal precipitation, unfortunately, for locations such as California, which desperately need the precipitation. Here's a final image as I close out this video from Virginia Beach back on the 28th of January 2021, showing the accumulated snowfall for the area. And here's where to find us on social media. Just take a look. We appreciate everyone again subscribing to the channel, and certainly hope you've enjoyed the winter weather outlook, and feel free to give us comments on the YouTube channel. And thank you so much again for subscribing, and we wish everybody a great evening. Hope you enjoyed the video. Take care, everybody.